3.5, continuity continued, and the IVT. So we have pictures of a continuous function and a non-continuous function. We talked about continuity earlier in the year. If a function is continuous at a point, then the y value at that point must be defined, the limit approaching both sides must exist, and the function point and the limit must be exactly the same. So just to review that, let's make sure we check all three of these things. We're trying to find where this is continuous. At 4, it's going to be continuous, or the y value of 4. Okay, that's at x equals 2. Everywhere else, x squared. X squared is continuous everywhere. So we just need to make sure that f of 2 equals the limit at x equals 2, because that's the only point where it could possibly be discontinuous. F of 2 is 4. The limit as x approaches 2, okay, from either side of f of x, plug 2 into x squared, that is 4. So since f of 2 equals the limit as x approaches 2 of f of x, since that is true, f of x is continuous for all x values. Okay, that's a fancy way of writing for all x values. Now, is f even, odd, or neither? Since it looks like this, with a hole and then the hole filled in, we know that f of x is even. Has y-axis symmetry. Okay, example 2, this one is a little bit more involved. So let's look at each of these functions. We know that this function has a vertical asymptote at x equals -3. The second function is linear, it's always continuous. Third function, a parabola, it's continuous. And the fourth function is a square root function that is continuous. So now the only other places where this function may not be continuous are at these numbers here. So we have to check each of those to find out if f of x is continuous. Alright, so what is f of -2? Let's check that out. Plug -2 in to this part. Okay, so we get -4 plus 5, that's 1. The limit as x approaches -2 from the left. So the left side, okay, smaller than -2, that's going to be 1 over x plus 3. Plug that in. 1 over -2 plus 3, we get 1. Now what's the limit as x approaches -2 from the right? This time we're looking at 2x plus 5. Plug it in, you get 1. So f of x is continuous at x equals 1, or x equals -2. Whoops. Okay, let's check another point, f of 2. F of 2 is 4. I plugged it into this part. Limit as x approaches 2 of f of x. Let's say from the left, smaller than 2. That'll be 2 times 2 is 4 plus 5, 9. Limit as x approaches 2 from the right. This time we're going to look at the x squared. That's 4. F of x is not continuous there. Okay, let's try f of 4. F of 4 does not exist. So the function f of x is not continuous there. Alright, so determine the values at which the function f of x is continuous. Let's answer that one. F of x is continuous for all x values, x real numbers, except x equals -3 because we have a vertical asymptote, x equals 2, and x equals 4. Everywhere else, it is continuous. Now let's finish this. Find the limit as x approaches negative infinity. Now we know that that function all the way on the left side, okay, the 1 over x plus 3, that's going to have a horizontal asymptote at 0, so that's going to be 0. The limit as x approaches infinity of f of x, the square root of x is going to continue rising slowly as x's get bigger, so that limit is actually infinity. Alright, next example, the graph is given below. Discuss and name any points of discontinuity. Alright, so it's discontinuous at the first spot I see, x equals 1. This is called a removable, because it's a hole, removable jump discontinuity, because it jumps up to another point. Okay, and let's see, we have also at x equals 2, which that would be a non-removable. If we put in one hole there, it doesn't make it continuous. Okay, that's a non-removable jump discontinuity. Okay, if we check the one-sided limits, you know, we see that they don't match the function values at those points. So based on the three-step definition of continuity to point, what can be said about the continuity of the endpoints? They would be discontinuous at the endpoints because we can only take one-sided limits. We don't know what's happening on the other side. We'll look into that more later as we get further into our calculus study. All right, so with this one, it's a little bit different. We're going to find the value to make it continuous. So in this case, we need to figure out what the function value is when we plug in -1. Okay, we're looking at this part. So plug in -1, we get a times 1 plus 1. So we have 1 plus a. Okay, we want the limits now to equal that. So the limit as x approaches -1 from the left of f of x, that's going to be 4 minus -1 squared, which would be 4 minus 1, which is 3. And we need to set that equal to 1 plus a. Okay, solving that, we get a equals 2. Alright, and just to double check, limit as x approaches -1 from the right this time. If we let a equal 2, so we have 2 times 1 plus 1, that should also equal 3, and it does, so we know that that is the value that will make this whole function continuous. Alright, I think we'll do probably one more example, example 5 here. Find the values of k so that the function is continuous. Alright, so what's happening? We need to figure out what's happening everywhere else. So if we take the limit as x approaches 4 but doesn't equal it, we're talking about this big function. I'm going to factor it because I think it'll make it a little bit easier. I know this can be x minus 4x plus 3. My thoughts are one of those will be a factor, x minus 4 maybe. And then I would end up with 2x plus 1. I believe that works. Tell me if I'm wrong. Now I know there's a hole at 4, but we're trying to fill in that hole and make it continuous. And so to do that, if we figure out this limit, plug in 4, we get 9 over 7. If we fill in the y value at 9/7, we will make this entire function continuous. Alright, so I think that's a decent place to stop. I would like you to try this. Okay, I'm going to give you what I got for A, and I'd like you to try it and put B in your whisk. But we'll discuss this in class. Have a great